I would like to introduce first speaker of our day session, Saak Gabriyelyan, with a talk, Algebraic and Geometric Methods of Analysis. Please, up to you.
Thank you very much. First of all, I want to thank to organizers, to Sergey, for, in particular, for invitation to take part in this conference. My talk is called A Banach Space Characterization of Sequentially Ascoli Spaces. This is about my recent article published in Topology and its Applications, and I would like to start from some basic definitions and motivations of those notions. Let X be a Tikhonov space. We denote as usual by CKX the space CX of all real or complex valued continuous functions on X endowed with the compact open topology. And recall that space, Tikhonov space X, is called a K-space if for each non-closed subset A, there is a compact subset K such that this intersection A with K is not closed in that compact subspace K. A map S from X to a Tikhonov space Y is called K continuous if each restriction F of A, here is a mistake, F not S, to any compact subset K of X is continuous. Let me recall also that X is called, the space X is called a KR space if every K continuous function on it is continuous. It is well known that space X is a KR space if and only if the space CKX defined above as a space of all continuous functions endowed with a compact open topology is complete in the usual way. Each K space is a KR space, but there are KR spaces which are not K spaces. For example, the real line in any uncountable power, for example, Aleph1, is a KR space which is not a K space. Here is a counterexample. One of the basic theorems in analysis is the Ascoli theorem, which states that if X is a K space, then every compact subset of the space CKX is evenly continuous. Even continuity means that the map from X to K is continuous for any compact subset of the space CKX. Nobel proved that every KR space satisfies the conclusion of the Ascoli theorem. So it is natural to consider the class of Tikhonov spaces which satisfies the conclusion of the Ascoli theorem. Following Taras Banach and my joint article, we call Tikhonov space to be an Ascoli space if every compact subset K of the space CKX is evenly continuous. In other words, X is Ascoli if and only if the compact open topology of the space is Ascoli in the sense of the book of McCoy and Tanto. There are Ascoli spaces which are not KR spaces. The first such known for me example is given in our joint article with Taras Banach. Another example is the space of continuous functions of the ordinal space omega 1 endowed with the pointwise topology. One can easily show that X is Ascoli if and only if every compact subset of CKX is equicontinuous. This means that for every X from the space X and each epsilon bigger than 0, there is an open neighborhood of U of X such that annotate. Such difference less than epsilon for all X point X from the neighborhood U and for any F. This means that equicontinuity, exactly that this difference does not depend on elements F of the subset H. This is exactly equicontinuous. Being motivated by the classical notion of C0 barrel local convex spaces, I defined in my article the much weaker, sorry. Much weaker notion. The notion of being a sequential Ascoli space. A Tikhonov space X is said to be sequential Ascoli if every convergent sequence CKX in CKX is equicontinuous. This notion is considerably weaker, and some counterexamples can be done. Every non-discrete P space, I put in that article, is sequential Ascoli but not Ascoli. So this condition is considerably weaker than the notion of Ascoli space. Ascoli and sequential Ascoli spaces in various classes of topological function and local convex spaces are thoroughly studied in several articles. One of Taras Banach and many other articles belong to me with some of my co-authors. A map T from a Tikhonov space X to a local convex space E is called bounded. If its image Tx is a bounded subset of space E. And as usual, local convex space endowed with the weak topology is denoted by E weak. This is subscript W, means weak topology. Our motivation is the following characterization of sequential Ascoli spaces proved in one of my articles. A Tikhonov space X is sequential Ascoli if and only if every K continuous. This means that this map is continuous on any compact subset and additionally bounded map from X to the Banach space C0 of all sequences convergent to zero and endowed with the uniform topology is continuous whenever it is continuous as a map from X to this Banach space endowed with the weak topology. So if we have K continuous bounded map from X to the Banach space C0 such that this map is continuous as a map from X to C0 endowed with the weak topology. Then the space is sequential Ascoli if and only if this map T is continuous as a map from X to the Banach space C0. So we have here a considerably stronger condition. From weak topology, we come to the Banach topology, norm topology of the space C0. Later, I come back to the theorem, posing some open problems. Now, to understand how to use theorem 5, we observe first that C0 is a subspace of the dual Banach space L infinity, which is dual space of the Banach space L little 1. Therefore, the map defined in theorem 5 can be considered as a map from X into the dual Banach space L infinity of the Banach space L little 1. Consequently, now C0 endowed with the weak topology is a subspace of L infinity, but endowed now with the weak star topology, because we have C0, dual space of C0 is exactly L little 1, and the dual space of L little 1 is exactly L infinity. So the weak topology of C0 is exactly the weak star topology of the space C0 considered as a subspace of L infinity of the space L little one. We can generalize this notion as follows. Let E be a local convex space. Denote by E prime the topological dual space. So this is the space of all continuous functionals on the space E. And set now the standard notation for the space E prime and do it with the weak star topology. With the weak star topology. Do not write all this expression. We write usually this. Now, let X be a Tikhonov space. A map T from X to the dual space is called weak star continuous, because we need weak star continuity, if T is continuous as a map from T to the space E prime endowed with the weak star topology. Endowed with the weak star topology. This is very natural definition, weak star continuous, if it continues with the space with the weak star topology. Any map from T, any map T from X into the algebraic dual, the space of all functionals, not necessarily continuous, defines an associated map, which defines as follows. GAM, also very natural definition. TE XZ is equal, by definition, the value of TX on Z. X belongs to X, so TX belongs to E prime, and Z belongs to E. So this definition is correct. And one can prove easily the following lemma, which states that a map, this map, is weak star continuous, what we need in what follows, to have weak star continuity instead of weak continuity to C0 space. If and only if the associated map TE is linear by the second argument, this is very clear, and separately continuous. This is some criterion which allows us in the proof of the main result to check only these conditions of lemma, this lemma. This lemma shows that the following notions are well defined. Let X be a Tikhonov space and let E be a local convex space. We shall say that a map T is almost K compact, respectively almost K sequential, if it is weak star continuous. This needs for us to obtain an analogy of the previous theorem. And there are a neighborhood U of 0 in E and a compact subset. This compact leads to related to K compact, this, and respectively null sequence, which related to K sequential, such that this family, the image of this neighborhood, is contained in the absolutely convex closed hull of this compact set. Here it is added the word almost, because the absolutely convex closed hull of A compact set need not be compact, so I added the word almost compact. Local convex spaces in which the absolutely convex closed hull of each compact subset is compact are said to have the convex compactness property. This is sufficiently well known and well studied property in local convex spaces. Now, I want to formulate the announced Banach space characterization of sequentially Ascoli spaces. For a Tikhonov space X, the following assertions are equivalent. X is an Ascoli, respectively sequentially Ascoli space. 2. For each cardinal gamma, every K continuous and almost K compact, the image is not too big, map T from X to L infinity gamma is continuous. And now we can replace L infinity gamma by any Banach space by saying that for each Banach space E, every K continuous and almost K compact, respectively almost K sequential map T from X to the strong dual Banach space, this is Banach space, is continuous. Numerous new characterizations of sequential Ascoli spaces, KR spaces, will be published soon in my recent article. Now I want to pose some open problem. Let me come back to theorem 5. A Tikhonov space X is sequential Ascoli if and only if every K continuous bounded map T from X to C0 is continuous whenever it is continuous as a map from C0 dot with the weak topology. So I do not know, can or not, in the previous theorem, in this theorem, main theorem, when we consider almost K compact, this means that those maps are weak star continuous replaced by simply continuity of this. So is it true that a Banach space X is sequentially Ascoli if and only if for each Banach space E, every K continuous bounded map T from X to E is continuous whenever it is continuous as a map from X into this space and dot simply with the weak topology. Let me note that in the previous theorem I formulated to the dual Banach space, here to any Banach space. So this is a considerably stronger condition. Is it true one can consider instead of any Banach space here, any Banach space, are replaced by a special class of Banach spaces CK. CK where K is a Banach, is a compact space. So this is Banach space over a compact space. This is what I wanted to tell. This question is, of course, of interest because it is quite symmetric and stronger than previous one. And this list of literature which I used in my talk. Thank you very much.
Thank you.